All right, section 2.3, we've been working with inverse trigonometric functions, and we had left off on examples 9 and 10 last time. We talked on examples 9 and 10 about the fact that in order to make these work, here we are, here, we actually have to make sure we're in the right quadrants, right? So let's look at 9 real quick. So in quadrant number 9, in problem number 9, we had taken a look at this particular value, negative pi. And since it's the inverse cotangent and we were looking at the domain values for inverse cotangent, they were negative infinity to infinity. This is our sort of reminder over here on the side. Negative pi is between them. So since negative pi is between them, we're able to cancel the inverse and the original cotangents out. They just cancel one another. It doesn't work quite as cleanly on this one. And the reason that it doesn't is because the 7 pi over 4 isn't in the domain. The domain is supposed to be quadrants 1 and 4. 1 and 2, 1 and 2, and this is in quadrant 4. And so we have to find the corresponding angle measure that gives us that same secant value in the correct quadrant. So since we're in quadrant 4, and we were looking down here at the 7 pi over 4, that's if we were going around it to the left, like counterclockwise, we identified that that's the same location as negative pi over 4 if we're going clockwise. That still puts us in the wrong quadrant, but it at least gives us the angle that we can flip up. So the secant values are positive when they're on the right-hand side of the graph in quadrants 1 and 4. So the secant will flip, or the angle will flip up, and it'll give us the same secant value if we're in quadrant 1. So that negative pi over 4 flips up to the top quadrant, and we're at pi over 4. Okay, so that's kind of where we left off last time. Does that sound familiar-ish? It's confusing, but does it sound like the things we were talking about? Okay, good deal. All right, so we're going to continue, and what you notice on these is that the problems change slightly. So what has changed on this problem based on the one we as compared to the ones we had before? So instead of having like sine and inverse sine, or secant and inverse secant, we have sine and inverse tangent, right? Like they aren't just opposites of one another. So I can't just cancel things out very nicely, even if I am in the right quadrant. It won't work that way because these are not inverse functions. However, what we do want to remember is that this is still measuring an angle. Okay, so inverse tangent of 7 over 24 is still finding an angle, and we can still rewrite it the way we were doing last time, so that the tangent of the theta is equal to 7 over 24. Now, we'll get back to the fact that there's a sign on the outside. We haven't done anything with that. But the part that's in the parentheses, the tangent being 7 over 24, actually allows us to create a triangle that we can work with. So when we're working with positive tangent, we need to make sure we are in the right quadrant. So what quadrant are we in if tangent is positive? Yeah, quadrants 1 and 3. And since tangent and inverse tangent only work in 1 and 4, we're going to be in quadrant 1. So we have this kind of a triangle showing up. Oops, that's not what I meant to do. Let's go with that. Okay, so this is my angle, or my triangle, with that being my angle. Okay, so I'm drawing the triangle in the correct quadrant. I do need to make sure I'm in the correct quadrant to do this, okay? And then 7 over 24. What is tangent in terms of triangles? It's y over x or opposite over adjacent, right? Either of those kind of descriptions. So if it's y over x, we could write this like our y value would be 7, our x value would be 24. Now that's not a unit circle value, but that could be an ordered pair, right? Or if you're thinking about it as opposite over adjacent, the opposite is 7 and the adjacent is 24 like this. So either of those versions would be perfectly reasonable. But now what I want, okay, so I've dealt with the tangent part. Done. That part's completely finished. Now I'm able to move out to the outside about sine. Okay, the sine part itself then needs to be the sine of this same triangle. Okay, well, what is sine in terms of triangles? Because it doesn't really help us now to look at our ordered pair. It's not just the y value, because this is not on the unit circle, right? The idea that the y value is the sine value works when we're on the unit circle, and this isn't the unit circle because this 24 and this 7 are not locations on the unit circle, okay? So we need to figure out on our triangle, we're going to push into triangles for sure, what's that third side? So how do I find the third side of the triangle? Pythagorean theorem, of course. So I'll have 7 squared plus 24 squared is, and let's just call it h for hypotenuse squared. You can call it something else if you wish. All right, 7 squared is 49. 49. Somebody's going to have to tell us what 24 squared, because that's not one I have memorized. What's 24 squared? Let me move this over here for some more space. 576. And what do you get if you add those two together? It is 625. And then what? Square root. And this is actually a nice one. What is the square root of 625? It's 25. This is called a Pythagorean triple. We've encountered some of them before. The 7, 24, 25 is a Pythagorean identity, the Pythagorean triple that has nice whole number values. So, excellent. So our triangle is sort of filled in now. And sine, in terms of a triangle, is what? It's opposite over hypotenuse. Well, what is the opposite in this triangle? 7. And what's the hypotenuse? 25. So when the trig functions are not inverses of one another, like this one, when one's tangent and one's sine, or any other two of them if they just didn't match, right? What we need to do is we need to be able to create the triangle, first of all, in the right quadrant. So we have to make sure we're in the right quadrant for this to work. And then we're using triangles to try and find the missing piece. We'll have one piece at least that's missing that we're able to work with. And then we're able to use the triangles to find the missing angle measure, or not angle measure, but the trig value that we're looking for. So this is sine of theta is 7 over 25. Okay, let's try another one. Yes, ma'am. All right, so tangent and inverse cosine, they don't match, just like the last one didn't match with the sine and the inverse tangent. So we're starting on the inside, same as we did before, and we're rewriting this as cosine of theta is 1/2, like this. Okay? So we need to set up a triangle. We need to make sure we're in the right quadrant. So what quadrant are we in if we have a cosine value that is positive 1/2? Yep, we're in quadrant 1. Okay, so here's our triangle. And cosine. In terms of triangles, what is cosine? Adjacent over hypotenuse. So I should put my angle measure in here. Sure, there it is. So adjacent would be this one down here, and the hypotenuse would be right here. Everybody good so far? All right, so we have the missing side we have to find. So we're going to call it, let's just call it A. So our a squared plus 1 squared is equal to 2 squared. So 1 squared is 1 and 2 squared is 4. A squared would be 3. So what will A be?
3.
Square root, yeah. So square root of 3, yeah. So we have square root of 3. So my third side over here is square root of 3. So once you've filled in the triangle, you're done with the part that's in parentheses. Okay, so we've sort of checked that off the list of the pieces that we need to accomplish. Now we're moving out to the outer part of the parentheses on the outside, which is tangent. So the tangent value will be based on the triangle. How do we find tangent?
Opposite over adjacent.
Right, it's opposite over adjacent. The opposite's square root of 3, and the adjacent would be 1. And simplified, that would then just be the square root of 3. So the tangent value would be square root of 3. Okay, are we good? Got one more of this variety for us to take a look at. So again, they don't match, right? That's kind of the section of material. And we start the same way. We start inside the parentheses with this whole piece equaling to theta. So the cosecant of theta is equal to 8. I don't know why I chose all positives. So since it's positive, which quadrant are we in? 1, right? We're in quadrant 1. So cosecant in quadrant 1. Whoops. What is the cosecant value? Or how do I put the 8 into cosecant? Because number 1, it doesn't look like a fraction. The other two look like fractions. And number 2, it's cosecant as opposed to one of the other ones that we have, one of these SOHCAHTOA pieces that we can sort of push into. So what do we do for this?
Sine and inverse.
Okay, so we can think of it as sine. Was that where you were headed to, Chloe? Yeah, and that's how I would think about it as well. I process sine, cosines, and tangents easier than the reciprocals. So if we changed this, what would this be the sine? If the cosecant is equal to 8, what is the sine? It's 1 over 8. Very good. Okay, so 1 over 8. And looking at then at my picture, where will the 1 and the 8 go? Here's my theta. The opposite, so that's the 1. And not adjacent, but hypotenuse. Yeah, so the 8 will go here. So the missing side, we'll call it b, just for another letter, right? So we have 1 squared plus b squared equals 8 squared. So 1 squared is 1. What's 8 squared? 64. And if we subtract, then the b squared's 63. And we can square root, right? Now that does simplify. It's not just square root 3. How will 63 divide out to simplify? How does it break apart? Yeah, 9 and 7. And you can actually pause there if you'd like. Sometimes people want to break the 9 down, which you can do. But 9's a perfect square, which means I can take a square root of it. So what's the square root of 9? 3. So I can pull the 3 out, and I can leave the 7 underneath. So 3 squared is 7. Okay, so the third side, the one that's missing down here, is 3 square root 7. And now I'm supposed to find the cotangent value. So this one's all full of uncomfortable trig values, right? Cotangent, what is the cotangent's form? Yeah, so tangent would be opposite over adjacent. So this one will be adjacent over opposite. You're right. So adjacent is the 3 square root 7 that we just found, and the opposite happens to be 1. So this one nicely just becomes the 3 square root of 7. All right, so there's one more piece in this section that we're going to take a look at. And it's kind of just a variation of what we've been doing. What looks different from this problem compared to the last 3? It's got an X in it. What happened in the last 3 problems? They were all numbers where that X is, right? They were all numbers. So the process isn't any different. We're going to do the same process, but it's not going to have numerical values when we're done. I'm not going to have numbers. I'm going to have something with some X's in it because this problem starts with X's in it. Does that make sense? Okay, now when we draw these, because we don't have any other given information to sort of lead us in another direction, we will draw them in quadrant 1. Okay, so we are going to draw these into quadrant 1, just like the other 3 that we had done because they were positives. And we're going to start with the inside, just like we did before. This will say that the tangent of theta is equal to, in this case, x. Well, x is the same as x over 1, so you can make it into a fractional sort of view that way. And what is tangent in terms of triangles? Yeah, it's opposite over adjacent. So here's my theta, right? So opposite would be straight across, and the top of my fraction is the x, and the adjacent underneath of my fraction is the 1, so it would look like this. Okay, like imagine if there were a number in the place of x. That's exactly what we would have done, right? Same thing. But now I have to find the third side. Now the third side's not going to give me a number, right? Of course it's not going to give me a number because there's an x as one of the sides of my triangle. So again, I'm going to call it h for hypotenuse. You can call it c if you want to for Pythagorean theorem. That's fine too. And we have 1 squared plus x squared equals h squared. Okay, does that make sense in terms of the equation? So you have to pause yourself and remind yourself, what am I looking for? Am I solving for x? Am I solving for h? You're solving for h. We want to find the third side of the triangle that we don't know. Okay? So when there's 2 variables, pause and ask yourself, which one am I solving for? And in this case, it is h. So the 1 squared is 1, that's fine. X squared can't simplify, it's x squared. So what will I need to do then to solve this for h? Yeah, I'm going to square root. So I'll square root, and then the square and the square root here, those are going to cancel one another out. And the h is simply going to be the square root of 1 plus x squared. There's always this temptation, even clear up to my Calc 3 class last semester, I have students wanting to do this because you kind of think, surely I can simplify. Surely I can do something to clean this square root of 1 plus x squared up. And the temptation is to say, well, let's just take the square root of each piece. That's actually not going to give you the right answer. You cannot distribute square roots that way. It doesn't work. And we could do a real quick example why, and I think I shall because I want to make sure that you remember this later. So let me take a look at one with you. Let's say that it looked like this. All right, what is 3 squared? 9. What is 4 squared? Good, and what's 9 plus 16? 25, nobody's talking to me, but it's 25, are we good? Okay, if I took the square root up here, and I took the square root of this one and gave you 3, and the square root of this one and it gave you 4, what would that give you? You'd get 7, right? But what is the square root of 25? It is 5. You cannot distribute square roots, all right? So this is one real quick example showing you why, with some simple numbers, which is kind of a nice one, but it never works, okay? So no simplifying square roots. Now, that's actually kind of a good thing, because anytime you don't have to simplify, it's one less step to do, right? Okay, so don't think that this is bad. This is actually good. It means you've got less work to do. So this one will be the square root of 1 plus x squared. Okay? You've got the 3 sides filled in. Once the 3 sides are filled in, we can move to the outer part, outside the parentheses. And the outside the parentheses here says cosine. So how do I find the cosine in a triangle? Yes, it is the adjacent over the hypotenuse. What is the adjacent here? It's the 1. And what's the hypotenuse? Square root of 1 plus x squared. And you actually get something else really nice happening. So if this had said square root of a number, like square root of 3 in the denominator, what would we have to do? We would have to rationalize, right? We don't have square roots in denominators in general, right, with numerical values because they're irrational. But the thing about this one is that depending on what x is, depends on whether this is rational or irrational. And because we don't know, we get to leave it. So the square root in the denominator is absolutely fine there. Now, if you go and you do that, you try to multiply top and bottom to eliminate and so forth, it's not wrong. But if you make a mistake while doing so, then it will be. Does that make sense? So we're perfectly fine with leaving radicals that have variables in them in denominators. Let's try another one like this. So this one looks a little bit messy just because we have a radical. In fact, it's interesting because the problem given to us actually puts the radical in the denominator, which is a little unusual. But we can work with it. There's not a problem. So as I mentioned before, where will we draw our triangle? Quadrant 1. You got it. So here's quadrant 1 going on. And my theta value, here we go. Okay, so we've got this piece right here. And this says the cosecant of theta is going to equal x over square root of 3. Now, we had cosecant before, and we did something different with it. We didn't leave it that way. What did we do when we saw cosecant before and tried to draw a triangle? Yeah, we changed it into sine. So if I change this into sine, what would this say for sine of theta? Good, square root of 3 over x. And you do not have to do that. You could deal with the cosecant if that's okay with you. I like the sine better, so that's how I usually think about it, but it's your choice. Okay, so if I deal with the sine theta is equal to square root 3 over x, where will the square root 3 go? Oh, I'm sorry, back, yes.
So it's when we're working with x, will it always just be in that positive?
Yes, when you're working with x, unless they tell you something otherwise, and I don't remember any places where they do, we're going to always draw it in quadrant 1.
Okay.
Yeah. Yep. All right, where will my square root 3 go as I'm setting up my triangle? The opposite. So square root 3 comes over here. And where will the x go? That's the hypotenuse. Okay, so this is the setup from the inside of the parentheses. What's my next step? Yeah, Pythagorean theorem. I got to find the third side. Give it whatever letter name you wish. I'm going to call it A this time. Then I'm going to have a squared plus square root 3 squared equals x squared. Oops. What am I solving for, x or a? I think I heard both. Which one is it?
A.
It is a, okay? X was given in the original problem. X is going to stay part of my problem. A is the one that I created, right? Like, and Mackenzie might have created, it's Mackenzie, right? JC, I'm sorry. JC might have created not that same value, right? She might have chosen to let it be B, right? So this is where there's arbitrariness in our work. So we want to eliminate that arbitrariness by solving for it. So we're going to solve for A. So a squared is going to be written, what's the square root of 3 squared? Ooh, that's just 3, right? They cancel. X squared. What would I do next?
Subtract 3.
Yeah, I'll subtract my 3. So this is now a squared is equal to x squared minus 3. Then what? Then we'll square root. And while it may feel like we should be able to simplify more, we won't be able to, right? This a will simply equal the square root of x squared minus 3. So down here, square root of x squared minus 3. Once I have all 3 sides of my triangle completed, I'm ready to move to the outside of the parentheses. And the outside of the parentheses says that I'm supposed to be finding cotangent. What is cotangent of theta? Good. It's adjacent over opposite. What is my adjacent? Square root of x squared minus 3. And what is the opposite? Square root of 3.
Would those square roots cancel?
So the square roots won't cancel, but we do have to rationalize something here. Why do I have, well, let me say first. What do I have to rationalize, numerator or denominator? Denominator. We always work with denominators in terms of rationalizing. Why do I have to rationalize this denominator when I haven't had to rationalize the previous one?
The square root.
There's an actual number. The square root in this particular denominator is an actual number.
Oh, so if it was x, we wouldn't have to take
Right. If this had been the denominator said square root of x, we would be fine to leave it that way. But because it's the square root of a number, we have to take it and turn it into a rational form. So what do I do to rationalize square root of 3 in the denominator? Right. So I'll multiply by square root of 3, top and bottom. Okay. Now on the bottom, what will that give me? That's the easy one. 3. That's the whole point. On the top, however, Beck, is I think it's going to do what you kind of were hoping you would get to do before. You can actually combine these on the top because they're both square roots, right? So I can actually take the 3 that's underneath the radical and I can move it underneath the other radical. Does that make sense? They're both under radicals, so I can merge them together. So in a very real sense, I can put the 3 underneath here and the x squared minus 3 underneath here. I can multiply them underneath the radical, and I can simplify that to being 3x squared minus 9 over 3. That doesn't look very pretty, and in fact, it looks very frustrating, to be honest. I see a 3, a 9, and a 3, and I can't cancel them. Why can't I? What did you say?
It's okay.
You're good with it. You're like, I don't care. I don't have to. Why can't I cancel the 3 and the 9 on top with the 3 on bottom?
It's a square root.
Okay, the top has a square root and the bottom doesn't, right? One piece is underneath the radical and one piece is not. That makes them different. I can't simplify them when one piece is under and one piece is not underneath the radical. So I am finished at that point.